In the upcoming units, we're going to talk about the atomic structure of an atom. We know that atoms consist of protons, electrons, and neutrons. Now we're going to dive deep into how the atoms are organized in the periodic table itself. We learn how electrons are arranged around the atom by studying the interaction between matter and different forms of electromagnetic radiation. Electromagnetic radiation has two parts. It has an electric part and a magnetic part that travel perpendicular to each other. Since it's radiated, it could have a medium, that means atoms present, or no medium. So for example, the sun gives us electromagnetic rays, and it is able to travel through a vacuum. In a vacuum, all EM waves travel at the speed of light. As more and more particles are present, or more medium is present, the speed of light slows down. This is the EM spectrum. It is arranged by its wavelength, or we could say by its frequency. The radio waves have the longest wavelengths. Radio waves consist of AM and FM waves, microwaves, then infrared. In between infrared and ultraviolet is the visible spectrum. The infrared is next to the red. The ultraviolet is next to the violet end. After ultraviolet, it is the X-ray, then gamma rays. As I go from left to right in this spectrum, the wavelength gets smaller. As the wavelength gets smaller, its frequency increases. So you have more frequency in a given unit of time. If you look at the visible light, the red has a longer wavelength, so a lower frequency. The violet light has a shorter wavelength or a higher frequency. For this class, you do not have to memorize the EM spectrum, but you need to know that the visible light is between 400 nanometers to 700 nanometers, in which the 400 nanometer is the violet light and the 700 nanometer is the red light. All EM waves are transverse wave. A transverse wave is in which the wave motion is up and down as it moves forward. Motion of the wave is up and down, so they are perpendicular to each other. The highest point of a wave is called a crest. The lowest point is called a trough. The height is called the amplitude and labeled A. And one of the most important part of the wave is called the wavelength. Abbreviation of wavelength is lambda, Greek letter. It is the distance between two consecutive identical points. So if I start with the crest, the wavelength is the distance from the first crest to the immediate next crest. If I start at the equilibrium point right here, it is to the next equilibrium point, in which they must travel at the same direction. If I start with the trough, it is to the next trough. That is the definition of a wavelength. So wavelength, speed of light, and frequency is related through the wave equation or the light equation. The speed of light is equal to frequency times wavelength. C stands for speed of light. You need to memorize this. This is a constant, 3 times 10 to the 8 meters per second. Frequency is nu, and nu is again a Greek letter. And if you notice, it looks like a V, but the V is written with the turn to the left. In physics, you would use F. Frequency is defined as the number of oscillation per unit of time. So what that means is, if I have a wave like this has less frequency because the wave is much longer. However, if the wave is shorter, you're going to have more frequency in the same, you're going to have a higher frequency in the same unit of time. So it's the number of oscillation per unit of time. The units of frequency is 1 over second, which can also be written as seconds to the negative first, or defined as Hertz Hz. Wavelength lambda, again, is the distance between two consecutive identical points, and the units are meters. You need to memorize these three prefixes, which will be common when we use the speed of light and the following equations. Nano is n is 10 to the negative ninth. You could easily memorize this because nano starts with n and 9 starts with n. Angstrom is capital A with a little degree sign on top, 10 to the negative 10th. You will see this sometime. It was common about 50 years ago. Pico, P is 10 to the negative 12th. One of the most interesting part of light is its dual nature. A light can behave as a wave or a particle. So when it behaves like a wave, it looks like a transverse wave. If it looks like a particle, it looks like little balls. So what is particle nature of light? Max Planck was one of the first physicists who described light as a particle. He stated that energy can be emitted or absorbed in discrete packets, and these packets were called quanta. And because of that, he said energy was a multiple of energy. So for example, if we have one quanta, that is energy, one energy. If we have two quanta, it's 2 times energy. If we have 5 quanta, it's 5 times energy. So these are individual whole number packets. So he came up with the Planck's equation, which stated energy is equal to h nu, in which energy E is in joules, or EV, which I will show you the conversion later. H is Planck's constant, which is 6.63 times 10 to the negative 34 joules times second. And remember, nu stands for frequency, units of 1/seconds, or hertz. Planck's equation was later used to solve for the wavelength of a light by incorporating the wave equation. So we know that E is equal to h times nu, and we also know speed of light is equal to lambda times nu, which is frequency. So you solve for frequency and plug it in. So if I solve for frequency, I need to divide both sides by lambda. So if I do that, nu is equal to frequency over lambda. So if I plug this in, this is h times c over lambda. So E becomes h, Planck's constant, c, the speed of light, divided by lambda, which is the wavelength of the particle. In this chapter, you will either use joules or electron volt. 1 electron volt is equal to 1.602 times 10 to the negative 19 joules. 1 electron volt is the energy required to accelerate an electron through a 1 volt potential difference. So let's try this first problem. UV radiation has a frequency of 6.8 times 10 to the 15 hertz. Calculate the energy in EV. So we know we're looking for energy, E. We also know the frequency, nu, is equal to 6.8 times 10 to the 15 hertz. We know that energy is equal to Planck's constant times the frequency, nu. Planck's constant is 6.63 times 10 to the negative 34 joules times second. My frequency is 6.8 times 10 to the 15 hertz. Multiply the two equals to 4.5084 times 10 to the negative 18 joules. So here the answer comes out in joules because there's a second on top. A hertz, remember, is 1/second, so they cancel out. It's in joules, but they want the answer in electron volts, so we need to convert it. So 10 to the negative 18 joules. Diagonal units have to be the same. This is joules. We know there's 1.6 times 10 to the negative 19 joules in 1 electron volt. So this equals 28.17. So if we do sig figs, there is only 2 because this is a conversion factor. So it only depends on the frequency. And the frequency, the exponent doesn't count, so there's only 2. So 1, 2, so this is 28 eV. So in this problem, we have a light with a wavelength of 525 nanometers. Calculate that energy. So we know the wavelength, lambda, is equal to 525 nanometers. So we're looking for the energy of the green light. We know that E is equal to h, Planck's constant, times c, the speed of light, divided by lambda. So all we have to do is plug in. So E is equal to 6.63 times 10 to the negative 34 joules times second. Speed of light is 3 times 10 to the 8th meters per second divided by lambda. So lambda is not in SI units, so we need to convert it. You could convert it outside and then plug it in, or you could convert it while you do the math problem. Since it's 525 nanometers, diagonal units have to be the same. So if this is nanometer, this is nanometer, we're going to go to base, which is meter. If I make the bigger prefix 1, then nano becomes a positive 9 exponent. If you make nano the smaller one, then the meters will be 10 to the negative 9th, which is the definition of nanometer. Either one works. I'm just going to use the one I wrote. If I plug these numbers in, this equals 3.788 times 10 to the negative 19th. So if I do sig figs, h doesn't count, it's a constant. Speed of light doesn't count because it's a constant. So it's going to only depend on the wavelength. So there's 2. Remember, conversion factors do not count. So 1, 2, 3. I look 1 to the right. So it's 3.7. Rounds up to a 9. And we must write the exponent times 10 to the negative 19 units of joules. Pause the video, try this problem on your own, and then check your answer. In this problem, there's multiple ways to do it. I'm going to look for the frequency first because it's the easiest. So energy is given as 1.4 times 10 to the negative 21st joules. And we could quickly find frequency because E is equal to h times nu, which is frequency. So at this point, if you're struggling with math, rearrange the equation. So to isolate frequency, we need to divide both sides by h. Nu becomes energy divided by Planck's constant. So I'm going to plug that in, 1.4 times 10 to the negative 24th joules divided by 6.63 times 10 to the negative 34th joules times second. This equals 2.1116 times 10 to the 12th, and it'll be 1 over seconds, which is a hertz. So if I do sig figs for this, there's only 2 sig figs because energy has 2. This is an exponent that doesn't count, and h doesn't count, so this is 2. 1, 2, I look 1 to the right, so 2.1 times 10 to the 12th hertz. At this point, there are 2 ways you could solve it. You could use E is equal to hc divided by lambda, or you could use the wave equation or the light equation, which is c times lambda nu. I'm going to use this one because it's a lot easier. So to isolate lambda, I need to divide both sides by nu. The nu's cancel out, so lambda becomes speed of light divided by the frequency. So speed of light is a constant, 3.00 times 10 to the 8 meters per second, divided by the frequency we calculated, which is 1.116 times 10 to the 12th hertz. So if I divide these two numbers, I get 1.42 times 10 to the negative 4th. And again, there are 2 sig figs. If your answer is a little bit off, that's fine because I carry all my digits to the end. So there's 2, 1, 2, I look 1 to the right, so it's 1.4 times 10 to the negative 4th, and this is in meters. So Einstein used Planck's theory of quanta and developed the photoelectric effect. This is what Einstein won the Nobel Prize for, not the theory of relativity. Einstein took Planck's quanta theory and stated that light behaves like energy packets, and he called these packets photons. He realized that light behaves like particles because to eject electrons, these electrons must meet a threshold frequency. So what Einstein did was get a piece of metal and he placed a red light above it and he also placed a violet light above it. No matter how bright that red light was and no matter how long that red light stayed on, no electrons were ejected. For the violet light, no matter how dim the light was, no matter how short the light was on, it ejected electrons. If an electron needs 2 electron volts to be ejected from a metal, so for this particular metal, the electron needs 2 electron volts to be ejected. When the red light is placed above the metal, no matter how bright or how long it shines on the piece of metal, the electron does not accumulate enough energy to be ejected. So that means the energy is not continuously absorbed to reach the 2 electron volts. However, when I shine the violet light above it, no matter how bright or short the light is, it has enough energy in it to eject the electron. His photoelectric effect stated that electron must meet a threshold frequency to be ejected from the metal. Another way you could think of the photoelectric effect is a baseball. The baseball is a packet of energy called photon. When I throw the baseball to you, you either receive the entire baseball or none of the baseball. It is not that I throw a baseball at you and you receive part of the baseball until you complete an entire ball. So when the red light is shining on the metal, it is not continuous. So the red light doesn't give me enough energy to throw or eject the electron to you. It is all or nothing. You either get the ball or you don't. How bright or short the light is, it has enough energy in it to eject the electron. His photoelectric effect stated that electron must meet a threshold frequency to be ejected from the metal. And remember, Planck's equation was E is equal to h, Planck's constant, times nu, which is frequency. If I look at the relationship between energy and frequency, the higher the frequency, the higher the energy. The lower the frequency, the lower the energy. So energy and frequency are directly related. So to meet the threshold frequency, I need to have a higher frequency light if red light does not work, because red has a long wavelength, and the longer the wavelength, the smaller the frequency. This is related by the wave equation. C is equal to frequency nu times wavelength. Since C here is a constant, my frequency increases, my wavelengths have to decrease because C must stay the same. If my frequency decreases, my wavelength needs to increase it by the same amount to make the speed of light constant. Bohr's model. Remember in first semester we said the Bohr's model was very similar to our planetary motion, in which the nucleus was like the sun and the planets orbit around the sun in fixed orbits, just like the electrons travel in fixed orbits around the nucleus. So Bohr took Max Planck's theory of quantized energy packets to explain the stability of atoms. He stated electrons have certain allowed energies, and since electrons have certain allowed energies, that means its electron cloud has a certain amount of energy. So if it has 3 joules of energy, it cannot have 2.9 joules. It cannot have 3.1 joules of energy. It must have exactly 3 joules of energy, and that electron that exists in that energy level must have exactly 3 joules of energy. So these electrons absorb and emit energy by moving from one energy level to another. And he related this by energy is equal to Planck's constant times frequency, or nu. He derived his own energy equation. Bohr's energy equation is delta E, which is equal to negative R subscript H Z squared, parentheses 1 over N F squared minus N naught or N initial squared. Delta E, remember, delta means change in energy in joules or electron volts. RH is the Rydberg's constant, which is 2.18 times 10 to the negative 18 joules. Z is the atomic number of the element. N subscript F is the final energy level. N naught or N subscript I is the initial energy level. In our first example, what is the energy associated with ground level state orbital N is equal to 1 for hydrogen? So we're looking for energy, and we know the ground state is equal to 1. So Bohr's equation is E is equal to negative RH Z squared 1 over N final minus 1 over N initial squared. Since there is no other energy level, this cancels out. So this becomes negative RH Z squared over N squared. So plugging this in, this is equal to negative 2.18 times 10 to the negative 18 joules. Hydrogen has an atomic number of 1 squared divided by 1 squared. So this is 2.18 times 10 to the negative 18 joules. If you notice, the energy in level 1 is negative. All the energy levels will have a negative value. The reason it has a negative value is due to something called Coulomb's law, which we'll discuss later. When a proton is attracted to an electron, it will have a negative value because a proton is positive and an electron is negative. What is the energy required for the electron to go from energy level 3 to energy level 1? E is equal to negative RH Z squared 1 over N final squared minus 1 over N initial squared. We are going from energy 3 to 1, so this is going to be my initial and this is going to be my final. I'm going to plug in negative 2.18 times 10 to the negative 18. This is still hydrogen, so it's 1 squared. My final is 1 over 1 squared minus my initial, which is 1 over 3 squared, equals to 1.937 times 10 to the negative 18 joules, and it is negative. For these problems, just carry a few digits after the decimal. You really can't do sig figs because Rydberg's constant is a constant. Z, which is atomic number, is usually a whole number, and the energy levels are usually 1 digit. So just carry a few digits. And if you notice here, it is negative in energy because it was jumping down from a higher energy level to a lower energy level, so the energy is being emitted. So the energy is being released. Here, for each energy level, it is negative because of its attractive force. So using the information above, solve for the frequency and the wavelength of the emitted photon. So pause the video, solve it, and then check your answer. So here there's more than one way to solve it. I am going to solve for the frequency first because energy is equal to h times frequency, which is nu. I'm going to take the absolute value of energy because frequency and wavelength are always positive, and the negative value in front of energy is because the energy has been emitted. Planck's constant is 6.63 times 10 to the negative 34th joules times second times nu. So nu becomes 2.9227 times 10 to the 15th. Since its frequency units is hertz or 1/seconds. At this point, you could use E is equal to hc divided by lambda, or you could use the wave equation or the light equation, which is lambda times nu. I'm going to use the wave equation because it's a little bit simpler. 3.00 times 10 to the 8th meters per second. Lambda times nu, which is 2.922 times 10 to the 15th hertz. So you have to divide both sides by the nu or the frequency, which equals 1.026 times 10 to the negative 7th meters. If you choose to convert this into nanometers, then it's 1.026 times 10 to the negative 7th meters. Diagonal units have to be the same, meters, nanometers. If I make the bigger prefix 1, the exponent is always positive. Remember, nano is 10 to the negative 9th. And so if you do the math, you get 102.64 nanometers. Pause the video, try this problem on your own, and then check your answer. So here we have energy in electron volts. So E is equal to 2.55 eV. And it's a hydrogen atom, so we know Z is equal to 1. And we're looking for the final energy when we start with the energy level and initial of 4. So we know we're going to use Bohr's equation. Delta E is equal to negative Rydberg's constant, Z squared, 1/n final squared, minus 1/n initial squared. So the first thing we need to do is convert the electron volts into joules. 2.55 eV, diagonal units eV, 1 eV is equal to 1.6 times 10 to the negative 19 joules. This is equal to negative R with H, which is 2.18 times 10 to the negative 18 joules, times 1 is the atomic number for hydrogen, squared, 1/n final squared, what we're looking for, minus 1/4 squared, which is my initial. There's one other thing you have to do here. Since the energy is released, you need to put a negative sign in front of delta E. We know we're going to look for something within this parentheses. Since this parentheses multiply by RH and Z, I need to divide them out to the opposite side to isolate that parentheses. So I'm going to divide both sides by negative 2.18 times 10 to the negative 18 joules and 1 squared. Same thing here, 2.18 times 10 to the negative 18 joules, 1 squared. So if I simplify the left side, you should get approximately 0.187155. And on the right side, this cancels out and it becomes positive. This is equal to 1/nf squared minus 1/16. So to isolate nf squared, I need to add 1/16 to both sides, 1/16. So 1f squared, so 1/nf squared is going to equal to 0.249655. And at this point, if you are stuck, cross multiply, because the denominator of the right side is 1. So if I cross multiply, this is going to be 0.249655 nf squared, and 1 times 1 is 1. So I need to divide both sides by 0.249655, 0.249655, and then I need to take the square root. So N final is equal to 2. So the final energy level is 2. So if you made a mistake here, there's 2 areas or 3 areas you would make the mistake. Remember, EV must be converted into joules because the constant is in joules. And you need to look for, is the energy being released or being absorbed? If the energy is absorbed, remember delta E is positive. If it's released, you need to put a negative in front or the math doesn't work out. And the last thing is make sure you square and take the reciprocal, then subtract. As I stated earlier, for Bohr's model, the energies are all negative for all values of N, energy level. The more negative the energy, the more stable the electron, the more stable the atom. When N is equal to 1, it is the most negative and most stable. When N equals 1, energy is equal to negative 13.6 electron volts. And remember, we stated it was negative because of Coulomb's law, because of the attraction between a positive proton and a negative electron. However, there was limitation to the Bohr's model. It only worked for hydrogen atoms. The Bohr's model provided 2 important ideas. One, that energy exists in certain energy levels. Number 2, in order for electrons to jump up and down those energy levels, they must absorb energy or they must emit energy. So particle nature of light says energy travels in packets called photons. De Broglie said that light can travel like a wave. He stated that each electron are associated with a particular wavelength. So if I have a nucleus and the electron orbits around the nucleus, when the electron orbits around the nucleus, it would behave like a wave, and this is 2 full wavelengths. If I start with the equilibrium point here, here's my crest, here's my trough, so that's 1 full wavelength. Again, I start with my crest, and then I go to my trough, so that's my second wavelength. And these waves were called matter waves, and they behave as whole numbers. So de Broglie came up with his own equation. He stated that lambda, or the wavelength, or de Broglie's wavelength in meters, is equal to h Planck's constant divided by the mass and the velocity. So h again is the Planck's constant. Mass must be in kilograms. We use the SI unit. Velocity abbreviation is a v, but my N goes to the right. My N goes to the left. Velocity is in meters per second. In physics, a mass times velocity is also momentum. And so you could also write it as h over p. So if I look at this equation, the mass, or how big an object, will determine its wavelength. The larger the object, it's going to have a greater mass. Since the mass is in the denominator, if I divide by a large number, my wavelength is very small. This is why, even though humans exhibit wavelengths, you cannot see it, because their mass is so large that if I divide by a large number, my wavelength is really tiny. If I have a small mass, like an electron, and I divide by a small mass, my wavelength is large. This is why we could see the wave of an electron using an electron microscope. So this tells us that de Broglie's wavelength is inversely proportional to the mass. As one gets larger, the other one must decrease. So let's look at our first example. What is the wavelength of an electron moving with a speed of 5.97 times 10 to the 6 meters per second when the mass of the electron is 9.11 times 10 to the 31st kilogram? So we're going to find de Broglie's wavelength, lambda, is equal to h mass times velocity. So h is Planck's constant, so that's 6.63 times 10 to the negative 34th joules second. Mass is 9.11 times 10 to the negative 31st. I do not have to convert because it's already in kilogram. And its speed is 5.97 times 10 to the 6th meters per second. This equals 1.219 times 10 to the negative 10th. Wavelength is in meters here. We could do sig figs. H is a constant. There is the mass of an electron is also a constant. So there's 3. 1, 2, 3. I look 1 to the right. 1.22 times 10 to the negative 10 meters. Pause the video, try this problem on your own, and then check your answer. So here we're calculating the velocity of a neutron, whose de Broglie's wavelength is 500 picometers. The mass of the neutron is given. So we know the equation is lambda is equal to h over mass times velocity. Again, if you're struggling, rearrange the equation. So if you're struggling with math, the first thing you want to do is cross multiply. The denominator of the wavelength is 1. So if I cross multiply, this becomes lambda times mass times velocity equals to the Planck's constant. To isolate velocity, I need to divide both sides by lambda and mass. So this cancels out. So velocity becomes Planck's constant, lambda times the mass. So we know Planck's constant is 6.63 times 10 to the negative 34th joules times second. The wavelength is in picometer. We need to convert it because we have to be in SI units. So again, you could convert the wavelength outside and plug it in, or you could convert in the process. So diagonal units have to be the same. Picometers, picometers, meters. I make the bigger prefix 1. So then this has to be a positive exponent, which is to the 12th power. And the mass of a neutron is given as 1.67 times 10 to the negative 27 kilograms. So this is equal to 794.01. We could do sig figs here too. So this is a constant, does not count. My wavelength has 1 sig figs because these are trailing 0. And then the mass of a neutron is a constant. So it's going to be 1. So I look 1 to the right. So my 7 becomes an 8. I need to put 2 0 as placeholders because the 7 is in the hundredths place and the units is meters per second. So Heisenberg developed the uncertainty principle. He tried to measure the position of an electron with a gamma ray microscope. What he realized that when the object is really small, like an electron, it is impossible to know both the momentum or the location at the same time. So you either know the momentum or you know the location, but not both. This leads us to quantum mechanics. This is the theory we currently believe. It was developed by Schrödinger. He developed a mathematical relationship which incorporated both the wave and particle nature of light. So he explained the duality of light by describing the energy states allowed by electrons. So the probability of finding an electron is, so here's a generic quantum mechanic equation. So Schrödinger's mathematical equation describes the probability of finding an electron in the electron cloud. This is a generic equation. These wave functions are known as psi, a Greek letter, and once we solve for this, you could figure out the probability of an electron in an electron cloud, which we learn is an orbital in the next video.